Good day, folks. This is tutorial number 16 in a playlist that I'm calling Elementary Problems in Structural Analysis using the 3D Experiences FEA module. Now, in this problem that you see there, it's a very simple 2D frame problem or beam problem, which is the left end is clamped and the middle point is on a roller and the right point is actually we're subjected to load. There's actually a spring sitting there. Now, I want to model that spring as a connector. The alternative is to model it with a spring element, but since currently I'm looking at the connector functionalities in 3D experience, I will be using connector. Now, connectors is where you do the meshing structural model creation. There is a tab here called connections, and at the very bottom, there's all kinds of connections that you can make, and one of them is a connector, of course. The other one is a spring. This is a pull-up menu. There's two items. They're rigid and spring, and the one that you want is spring. Oh, well, I'm not using it in this tutorial. I'm using connector. Now, this problem is done with two elements in an elementary book by Logan, the first course in finite element method. And he is using two elements, one going from the left point to the support, roller support, and then the other one from roller support to where the spring is. And he's using the two-noded but cubic elements. We'll come to that later on. Let's assume that the properties are standard steel. I'm solving a linear problem. And in that calculation, that fundamental calculation, hand calculation, the value of I, second moment of inertia about the bending axis, is given to be this number. Now, what I have done instead, I will be making a circular cross section. However, this radius will give you the same I, so the effect will be the same. The stiffness of the spring is given there, and the load is 50 kilonewton. Now, when it comes to creating connectors or even spring, there are two options. You can make the ends of the spring as two separate nodes, or the ends of the two connectors as two separate nodes, or you can actually collapse it to a single point, but that's not what I'm going to be doing. I'm going to be modeling it like that. As far as numbers go, answers go, it makes no difference. However, I rather see my spring. Okay. And for that, I'm going to be using the axial connector, because axial connector has the ability of modeling a spring buried inside of it and a damper, by the way. So when you create the connector icon, you select the two endpoint, the top point and the bottom point, and you change to get the axial spring, to get the axial connector, you have to change the type to specify. And there is the axial, if you use a pull-down menu, you select for translation axial. And of course, for rotation, we're not worried about it, so I selected none. Now, notice that you may have to select an axis system, but in the event that these two points are separate, different, okay? It's not that they're the same point, and it's not that one is a point, the other one is the ground. As long as it's not like that, as long as it's two separate points, this is irrelevant. It doesn't matter what you do, what axis system you give it, what orientations are, it makes no difference, because once the 2 points are separate, the direction, local direction, goes from one end to the other end, and that's fixed. Now, to specify the stiffness and a few other things, you just click on that pencil. You want to specify the stiffness of the spring, so you click on this elasticity line here. Don't try to click on the box. It's elasticity, and this thing shows up. You put the appropriate number there, and you may have to put 200,000 Newton per meter, because I'm not sure if there is an option for kilonewton per meter. I'm not sure. And then you click on the reference length. Now notice that right now the 2 points are selected to be different points, the top point and the bottom point for the spring, for the connector. But the reference length is something that you can specify. For example, if I've selected geometry like it is, and I say that the reference length is 1,000, means that before it actually loaded, there's no force in that spring, okay? If you put a different number here than 1,000, means that there's either a, because the distance of the top and the bottom points is 1,000, and the reference length, if it's less than 1,000, means that it's either compressed or it's, if it's bigger than 1,000, it's stretched. But that's not what I'm doing. I'm putting 1,000 here so that in the initial configuration that I showed you, there is no spring force. Okay. So the way it's done in Logan, these are the answers that they get. Rotation here, rotation there, and displacement, that's the compression of the spring. And these are the reaction forces. Okay, of course, this is not the reaction force. This is the applied concentrated force, and this is the spring force. Of course, they should balance out, and they do. And here's the documentation from the Abacus program, because after all, buried in 3D Experience is the Abacus program for the FEA solver, the default solver. And if you want to see what the axial, axial connectors, etc., it'll send you actually to the Abacus program, Abacus manual. Okay, and also notice that the orientation definition will be ignored if the two nodes are separate, like what I did. Remember, there are two top point and the bottom point, and they're separated by 1,000 millimeters. Now, and here's a few more things. Now, the only thing is that when it comes to modeling this thing, there are many different ways. And this in this playlist, tutorials 1 through, I don't know, 14, 15, I'm investigating different strategies. So what I'm going to do here is this. I'm going to make a line from the wall to the roller, and another line from the wall, from the roller to the right side. Okay. And I'm not going to join them. You will see what that entails. Now, this kind of a thing appeared in the previous tutorials. As I said, tutorials, I don't know, maybe 1 through 12, 13, etc. I'm not going to repeat that. Okay, let's go ahead and do this. So I started in generative shape design, or it could have started in part design. It makes no difference. So line, point and direction. The point I'm going to make 0, 0, 0. The direction in the y direction. Oops. Yeah. Okay. Direction in the y direction. Separated by. It says 3 meters, so in millimeters it's going to be 3,000. 3,000 millimeter. So here's my first line. Let's do another one. There is the wall. There is the roller. It will be actually line. Another one from this point. Y direction. 3,000 millimeter. Say okay. So I have two lines here. Then I'm going to create a point down below this, which is 1,000 millimeter below. So that's the bottom of the spring. So here's a point. Y is going to be 6,000. And Z is going to be minus 1,000. Okay. So there is the point that I'm talking about. Yeah. Right there. You can see that. Okay. Now, that's pretty much it. Let's apply material properties here. Notice that I'm not joining these, okay? So we go to tools, we create a material. And I'm going to call it Logan's example. Logan's example. This is September 21st, 2024. Okay. So we say, okay, it's going to create in the database. This and close that. It's going to create in the database, but no numbers are in it. So after I apply to this part, then I'm going to put my numbers in it. Okay. There we are. Let's take this thing, put it on that. I'm going to close that and just put in our numbers there. Okay. So it is a structural, abacus multiphysics, mechanical, elasticity, elastic, and it says 210 gigapascal, 210 GPA. It's going to convert it to PSI because my units are on PSI default units right now. And Poisson ratio is 0.3. Okay, good. That's pretty much it. Let me do a quick save here. Okay. Then we're going to do the meshing. Okay. That's as far as the model's creation is concerned. This is pretty much it. And I want to remind you, when it comes to meshing, you can do it like this. You can put the cursor here, right click, insert, and you can do a finite element model, or you just go change it to the appropriate application, which is structural structural model creation. It does the same thing. That's fine. It's an empty FEA model. Now, here's the meshing tab. You click on it, click on B mesh, select this. Because these do not join these two lines, you have to mesh them individually. Okay, line 1 has to be meshed, line 2 has to be meshed. You select the line 1. The size of the mesh, I'm going to make it 3000 millimeter because I want a single element from going from the wall to the roller support. 3000. Now, there is a box here. Right now, look what happened. When I mesh this thing, no problem. It's going to mesh this thing as single element. Okay? So I say mesh, and one element has been created here. You say okay. Now I repeat this. For that line, 3000 millimeter, a single element from here to here. But because these are separate lines, I did not join them. There will be a node on the left side and a node on the right side, which are different, unless this checkbox is, this box is checked. You see, it says any two things which are within 1 millimeter of each other, any two nodes which are 1 millimeter of each other, they're going to be merged. Now, for the first one, it didn't matter because that was the first node that's going to be created. But for the second time that I'm going to mesh this line, there is going to be a duplicate node, which is exactly at the same location. In fact, it meets that criteria, and therefore there will be a single element, a single node constructed there. So we say mesh. If this is not checked, there's going to be two separate nodes. Or if this tolerance is different, it's very, I mean, actually for this present problem, tolerance doesn't matter, but it won't let you put 0 anyways. Say mesh, and it's okay. Now, how do we know what this is actually worked? Well, let's select this. See that? It says, show me the visualization, numbering visualization. You click on it. That's fine. Let me update first of all. Okay. Now, numbering visualization. You see, if I put the cursor there, I select this, it says number 2. If I go on the other side and select it, it also says it's number 2. Okay, so that's good. Yes, very good. Now, I will create a group here which has this node in it. Okay, so this is node number 1. This is node number 2. This is node number 3. So click on the group, and I'll talk about this thing later on. Manual group, and I put the cursor here. It will select one node, and obviously that's node number 1. I'll talk about this thing later on after we run. Good. So that takes care of this. Now, we have to create connections. So we go to, sorry, actually, let's do the beam section properties. So we go to properties, and first of all, define a profile. I said I'm going to make it circular, and radius 120 126.3 millimeters, 126.3 millimeter. Now, this will give you a cross-sectional moment of inertia, same as what Logan has. Okay, say fine, and apply beam section. Because it's not joined, I have to do this thing one by one. Actually, I can select both of them. It's going to do it at the same time. But make sure it's a beam profile is selected. Very often people forget about that. And I say, okay. Now, if you want to see whether it was done correctly or not, so what you can do is you can click on the display, click on display preferences, and instead of non-beam profile, say, for example, solid. You can see that right there. It's done. I'll put it back on. Good. All right. Now, then we go to connections. Notice that at the very bottom, you have the different connections that you want. This is the connector. I want a connector here. See that? Connector. All right. So where am I in the slides? I'm right there. Okay. Now, for the support one, I'm going to select this bottom point. For the support two, I don't want to use ground. I want to use this. So there's two separate nodes, two separate points, vertices. You change this thing to specify, and for the translation, select axial, and of course rotation, we don't have any, we select none. Go scroll up, we get none. Good. Notice that there is an option of choosing coordinate system here, but it's totally unnecessary because these points are independent or not coincident. So this is direction one. I don't have to do that. Even if you selected stuff, created local coordinate system and selected, etc., it makes no difference. The answers will be the same. Now, here is the pencil that I was talking about. You click on it. Don't try to click on this box. Click to one next to it, elasticity, and you click on this. Click on the FX so that you can put the number there. Now, let me show you what happens. If you tried to type, for example, stiffness of 200 KN underscore M, it's going to come back with an error message. So I don't understand this. All right. So what I'm going to do is I'm going to say 200,000. 200,000. That means the kilonewton. You put 3 more zeros here and put an M there. Now this is going to get converted to Newton per millimeter, and it's going to give me the same number, 200 Newton per millimeter. Fine. Now we go to the reference line. Don't click on this box. Click to it next to it, and it's 1,000 millimeter reference line. And then we say OK. Good. And then we say OK. All right. So we pretty much did this stuff. Now we're going to go and apply our things. Okay, so we have to go and go to the structural scenario creation when we apply the loads and the restraints and things like that, boundary conditions. You select your model, FEA model, and obviously it's a structural problem. Okay, good. Now, the type of analysis is linear because this is what Logan does, and this is what we're doing in these tutorials. So you click on the procedure, scroll to the right. That is this. What is that? Static perturbation. That means linear analysis right here. See that? Linear. Okay, good. Say all right. Now, boundary conditions. So the boundary conditions, clamp. This end is clamped. Now, and this bottom point is also clamped. Say okay. This is on a roller, so we don't clamp it. We go to fix displacements. Now, I will not put it on that point, but I will come back and make a comment later on. So let's put it on the group that we created. Group. This is the one that I created, right? Excuse me. Okay, this can slide in the y direction, so that's free. X and Z translation on check. It can freely rotate about the x-axis, global x-axis, and these should be checked. So, okay, there we are. And that's pretty much it. Oh, load. You click on the load stop, a force on that point in the negative direction, minus 50 kilo Newton, which is going to convert it to thousands, 50,000. Very good. There, you can see that. Okay. So, all right, let's do a quick save. Because I think, unless I forgot something, we have taken care of everything that was needed. Okay, good. So we go to simulate. If you want bending moment, shear force diagram, and things like that that were discussed in earlier tutorial, you go to output displacement. Actually, I don't want to draw those things, but at least I want to get the reactions and things like that. You click on the force. There are some default ones, but these have to be requested. N force, nodal force, nodal force reactions has to be asked for. Otherwise, certain things that you can't get. You say fine, very good, and then go to simulate, model, and scenario check to see if there are any obvious things that we may have forgotten. Yes, looks good. Simulation check. Say okay. This is not running yet. It's doing a check on the simulation functionalities, whether they're properly indicated or not. So there are some warnings, but that's okay. And once this is done, then we're going to simulate, which means run. Almost done. Good. That's done. And now we're going to simulate which means we actually run. This is a simple linear analysis. It's done in one shot, just like Logan is doing it, time calculations. So, and we're going to compare the deflections and the rotations with what Logan gets. Okay, extracting results. And I'm going to plot the deflections. Okay, good, good. We'll close that. Let's change the deflection. Displacement. And you might say, well, wait a minute. This says 15.4. Maximum deflection of 15.4. Didn't we say that Logan is getting 17.4 millimeters? So why is it different? Well, let's go back here. And let me go to my finite element model right here. See that? Element type. Double click on this. It says element is type B31. We want B33. B31 is linear two-noded. B33 is cubic two-noded, which is what most FEA books use, such as Logan. Now we say, okay, and run. I'm not going to check things. I'm going to run. Because all I did was to change the type, and I better get 17.4 millimeters. Yeah. Otherwise, I miss something. Or Logan is wrong, which I don't think so. That's a well-known book which has been around for maybe 25, 30 years, and they have checked a lot of stuff. Remember, this is only 2D, two elements. Now, I want to tell you that there are other software which actually does frame and trusses and things like that, which civil engineers use. It's not. This is general purpose finite element program. There are programs such as SAP, or ETABS, etc., specifically for beams and trusses, and they, run a lot faster, but they're really specialized. This is a general finite element package, abacus, which is buried inside of 3D experience. You cannot separate the two because inside the 3D experience, the solver is abacus program. Done. Right here, 17.5. Excellent. 17.5, 7.48, etc., which was found. Now, if you want to see the rotations, so what we're going to do, by the way, the reason it looks like that, because there's only two elements. If this was not two elements, maybe 20 elements, this will be curved like this. But two elements, there's not much you can do. Now, if you double click on this, and you go to, instead of translation, so rotation, translation rotation, and then you say apply, and then if I put the cursor there, obviously rotation is 0. This is the wall. Rotation there is going to be 00249. 00249. If you put the rotation, if you select for rotation this one, 00748. 00748. Good. What about reaction forces? So we go back here, double click on this. I don't want displacement, so the best way to change this template to forces, it shows you only the stuff related to forces. So yeah, so let's go reaction forces. Okay. Nodes, magnitude, apply. Let's check something. If I put the cursor here, it says 6.94 e to the 8. This is a Newton, so it's going to be 69.8 Newton meter. I'm sorry, yeah, 69.8 Newton meter. 69.8 Newton meter. A kilonewton meter. Oh, sorry, this is a reaction. Sorry, this is a reaction. Oh, yeah, this was a reaction. Okay, 69.9 kilonewton. Good, good. And then you can plot the rotations. Now, let me go back here, and I told you something that, remember I created this group there? Let me do it differently. Let me go back there. Let me go to this loads boundary condition. This was the roller. Double click on it. Okay. Right now, it's on that group. Let me change this thing, remove this thing first of all, and instead go and select this point. It'll do it. It'll take the point. It took a vertex. And I say, okay. And let's go try to run it. Let's see what happens. Sometimes creating those groups is going to be very helpful. And sometimes maybe unnecessary. For example, notice that at the right endpoint, I did not create a group, or left endpoint at the wall, I did not create a group. But here I create a group. I want to show you, and the Abacus program, they don't call them group. Those of you who may be Abacus user, they're called sets. Okay. But in this particular problem, it didn't matter. I could have put it there. So if we get 17.4, sometimes you select things and it says that the support is not right, etc., etc., and then you may have to go direction of creating groups. But it worked here, irrespective. I'm pretty sure this is going to come out to be okay. I don't want reactions. I want displacements. 17.5. So in this particular problem, it doesn't matter, but in some of the tutorial, I've shown you that you really need to uh, create a group and do that. All right, folks. So that takes care of this, and good luck.